Okay. Okay. So now, that's all we're going to say about sequences. Okay. So that's all we're going to say about sequences. Put it away. Put it away. Thank you. Okay, that's all we're going to say about sequences. Now we're going to get to the kind of the important part. I mean, that was important for us to get to this next part, which is so-called infinite series. Okay, so infinite series. Okay, and so infinite series, what this is you have some sequence. So you have a sequence. A sub n, and you are interested in the infinite sum, a1 plus a2 plus a3 plus, oh wait, this is the wrong one. a3 plus a4 plus a5 onwards to infinity. Okay. Okay. So, right, and like we saw last time, this could be trouble, right? If we're not careful, then this can lead to all sorts of trouble, like 1 equaling 0 or 3 equaling 2 or this sort of thing. So you want to be careful about this. And so you think, you know, like somebody gives you, so example, what should 1 plus a half plus a fourth plus an eighth plus a 16th plus, what should this mean? What should this mean? What do you think about this? 1 plus a half plus a fourth plus an eighth plus a 16th, etc. What do you think that should be? What should that mean? What do you think that should be? Well, you know, if I have, and this is 1 plus a half squared plus a half cubed plus a half to the fourth, etc., etc. Right? The sum is so if we look at it like this, let's say here is 1. Right, so if we have 1, we're here, we add on a half, right, so this is 1, 2, we add on a half, and we get to here, we add on a quarter, we get to here, we add on an eighth, we get to here, we add on a 16th, we get to here. You see what we're doing, right? Right. Every time we add on a term, we're halving the distance to 2, right? And so maybe the way you think is that this ought to be, you know, maybe this ought to be 2. Should this be 2? Right? Maybe this should be 2. Okay. Yeah. So think about what you're doing when you do that. When you say that, the reason we said that was because when we added on, what we did was we started with 1 term, and then we added 2 terms, and then we added 3 terms. And then we added 4 terms, and then we added 5 terms, et cetera, et cetera. And we saw that that as we kept on adding on 1 more term, the numbers got closer and closer to 2, right? Right. So so that gives us that leads us to the following idea. Okay. So given a sequence a sub n, we define something called the sequence of partial sums. Okay, it's sequence of partial sums. Okay. Anthony, do you mind closing the computer? We define its sequence of partial sums. What that's going to be is the first thing is going to be A1, the second guy is going to be A1 plus A2. Third one is going to be A1 plus A2 plus A3, and so on and so forth, right? So we're going to call this thing S1, we're going to call this thing S2, S3. Sn is going to be A1 sum through An, etc., etc. Okay? So we define this thing called the sequence of partial sums, right? Sn, where Sn is defined to be the sum of Ai from 1 to n. Okay. Everyone okay? Okay. There's this thing, the sequence of partial sums, and it's the definition. Given the sequence A sub n, if the sequence of partial sums, if its sequence of partial sums converges to some L, we say the infinite series the sum of A sub I from 1 to infinity, converges to that L. And write the infinite sum is L. Okay, so let me give you some examples. Example 1, let's say that A sub n is n. Okay. What's S sub n in this case? If A sub n is n, right, A1 is 1, A2 is 2, A3 is 3, blah, 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 right? S sub n is going to be, who knows it? In factorial? No? And factorial? No. No. It's not in factorial. Right? Right? So here you've got, right, A1 is 1, A2 is 2, A3 is 3. S sub n, remember, is the sum of the first n terms, right? It's the partial sums, right? So it'll be A1 plus A2 plus up to AN, right? So S1 is going to be 1, S2 is going to be 1 plus 2, S3 is going to be 1 plus 2 plus 3, etc., etc. Right? So it's not factorial, it's the sum of the first n terms, not the product, right? Sn is going to be 1 plus 2 plus 3 plus n, that's n plus 1 over 2, right? Etc. Right? So that's your partial sum series, partial sum sequence. Okay? And you see what happens, right? As n goes to infinity, this thing goes to infinity also, right? It becomes infinitely large, right? And so we say that the sum of n from n equals 1 to infinity diverges. Right? It diverges. It doesn't converge to any finite number. Okay. Second example. A sub n is 1 over 2 to the n. Okay. A1 is 1/2. A2 is 1/2 squared. A3 is 1 over 2 cubed, etc., etc. S sub n right? S of n is here going to be 1/2. S1, sorry, is going to be 1/2. S2 is going to be 1/2 plus 1/4. S3 is going to be 1/2 plus 1/4 plus 1/8, etc., etc. Right? If you think about it a little bit, you see that Sn is actually 1 minus 1/2 to the n. 1 minus 1/2 to the n, right? This is 1 minus 1/2. This is 1 minus 1/4, right? This is 1 minus 1/2. This is 1 minus 1/4. This is 1 minus 1/8. In the end, you get 1 minus 1/2 to the n. Okay? And what happens to that? As n goes to infinity, that becomes what? As n goes to infinity, S of n becomes 1, right? And so we say the sum of 1/2 to the n from n equals 1 to infinity equals 1. Right? Okay. So, this is a shorthand, right? It's not saying the sum of an infinite number of numbers is 1. Okay. What it's saying is that the limit of the partial sums of this sequence is 1. Okay. It's a different thing, right? We have no real way of summing an infinite number of numbers, right? What we do have, though, what we can do is look at the partial sum sequence and see where that tends. Okay. Okay. So let me make sure okay. Another example. A sub n is 1/n minus 1/n plus 1. So A1 is 1/1 minus 1/2. A2 is 1/2 minus 1/3. A3 is 1/3 minus 1/4, etc., etc. Right? So this is actually 1/n plus 1. Okay. I'd like you to take a minute and tell me what Sn is. What's S sub n? Are you done? You're done. Okay. Talk to somebody nearby. Tell them what you think. Okay, who can tell me what it is? The sum of the first n terms is? 1 minus 1 over n plus 1. How many people, everyone get that? Did anyone get that? Great, that's right. Because you see what happens, right? If you look at S2, right? S2 is A1 plus A2. That's 1 over 1 minus 1/2 plus 1/2 minus a third, right? These guys in the middle cancel off and you're left with 1 minus a third, right? S3 is going to be A1 plus A2 plus A3. You see that's going to be 1 over 1 minus a half plus a half minus a third plus a third minus a fourth, right? Again, these things collapse and you end up with 1 minus a fourth, right? And so on and so forth, right? Okay, so that's going to happen up to here. And so the sum of these guys is 1 minus 1. The nth term of the partial sum sequence is 1 minus this, right? And as n goes to infinity, what do you get? 1, right? So what does that tell us? That tells us that the sum of numbers from 1 to infinity, 1 over n plus 1, at least it tells us this infinite series converges to 1. The infinite series, 1 over n plus 1, converges to 1. Okay. Okay. Another example. Fix a number r in the reals. Okay, fix some real number r. Okay, and let a sub k be r to the k. Okay, so our sequence where k goes from 0 onwards. Okay, so a0 is r to the 0, a1 is r, a2 is r squared, a3 is r cubed, etc. Okay. Then the nth partial sum is going to be the sum of the first n terms. So it's going to be a naught plus a1 plus a2 plus a n sub minus 1, n minus 1. Right. So that's going to be 1 plus r squared plus r to the n minus 1. So you have, here's your sequence, right? And here is your partial sum sequence. Okay. Okay. Does anyone know the trick of simplifying this? There's a trick to make this a little bit cleaner. There's an algebraic trick that you can play to make this cleaner. Anybody know it? Nope. Yes? No? Okay, so here's the trick. So trick to simplify S sub n. Consider R S sub n. Okay. R S sub n is, right, S sub n is 1 plus R plus R to the n minus 1. R S sub n is going to be R plus R squared plus r to the n minus 1 plus r to the n. Right? If you multiply this by r, everything gets shifted over by 1. Right? Okay, and then subtract. On the left-hand side, you get 1 minus r s of n. On the right, you get 1 minus r to the n. Right? And so that gives you a simpler way of writing s of n. It's 1 minus r to the n over 1 minus r. Okay. Now, what happens to this as long as r is not equal to 1? Right? If r is equal to 1, then we can't divide. But if r is equal to 1, then the partial sums are easy. Right? It's just going to be 1 plus 1 plus 1 plus 1 plus 1. Right? So it's just going to be n. Okay. 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 So what happens to this as n goes to infinity? Right? As n goes to infinity, what happens? The answer is, it depends. It depends on r, right? Depends on r. If r is small, so if the absolute value of r is smaller than 1, then what's going to happen? It turns into 1 over 1 minus r. Okay. Right? If r is, absolute value of r is bigger than 1, then it diverges. Right? If r equals 1, we already saw that it diverges. And if r is negative 1, it's easy to see that it diverges also. Okay. So that's interesting. So what we get in the end is what's called the geometric series formula. That the sum of r to the k, from k equals 0 to infinity, if the absolute value of r is smaller than 1, then this turns into 1 over 1 minus r. This is a very, very famous and often used formula. Okay, it's a very useful formula in mathematics. Okay. So, for example, if I say, what is 1 plus 1/3 plus 1/3 squared plus 1/3 to the 4th plus blah blah blah, right? What's that going to be? Well, that's just going to be 1 over 1 minus a third, right? So that's 3/2. Right? So this infinite sum is going to tend to this in the limit. Okay. Any questions? Any questions about that? That's pretty important. Pretty important. Let me give an example, sort of standard sort of example about this. So suppose I say, what is 0.999999999? Right? What is that? Right? You can think of that as 9/10 plus 9/10 squared, 9 over 10 cubed, plus 9 over 10 to the 4th, plus etc. Right? Right? You can think of that as 9 times 1/10 plus 1 10 squared. Actually, let me pull out an extra 10. Let me pull out an extra 10. So 9/10 times 1 plus 1 over 10 plus 1 over 10 squared plus blah, blah, blah. Okay. But what's this? This you recognize is a geometric series, right? This is a geometric series, and so this is going to be 1 over 1 minus the ratio, right? In other words, 1 over 9/10, and so you end up with 1. Okay. Maybe one way of making sense, this is a way of making sense of repeated infinite decimals. Okay. Okay. Last important example, something called the harmonic series. The harmonic series. Okay. So that is the sum of 1 to the n, 1 over n, excuse me, from n equals 1 to infinity. Okay. What do people think is going to happen to this? 1 over n, n from 1 to infinity. Right? Yeah. 1 plus a half, plus a third, plus a fourth, etc., etc. And so my question is, do you think it's going to converge, or do you think it's going to diverge? Can it be a finite number or an infinite number? Do you think infinite or finite? You think a vote? Who says it's going to be finite? Who's thinking it's going to be infinite? The answer is, it's infinite. It turns out to be infinite. Okay. There are a couple of ways you can see this. One way, okay, so I'll show one way. So, right, so you have, think like this. S1 is 1, right? S2 is 1 plus a half, right? S4 is 1 plus a half plus a third plus a fourth. S8 is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, right? And so on and so forth. Okay. So let's look at, so consider s sub 2 to the n. Okay. Consider, you don't have to consider everybody, let's just consider some of these guys. Okay. Okay. So this thing right here is three halves, right? Here we have 1, here we have 3 halves. If we look at the fourth term, we have this 3 halves plus these 2 guys, right? But these 2 guys, this is bigger than 1 plus a half plus a fourth plus a fourth, right? If I switch this third for a fourth, it gets smaller, right? Right? So this is 4 halves. What am I going to say next? What happens next? This is going to be bigger than what? Anyone see it? Anyone see the pattern? What am I going to do with these last 4 guys? I'm going to turn them all into 1 over 8, right? So I'm going to say this is bigger than 1 plus a half plus a fourth, plus a fourth, plus an eighth, plus an eighth, plus an eighth, plus an eighth, right? And that gives me another half. It will be 5 halves, right? You see what's going to happen. S16 is going to be bigger than 6 halves. S32 is going to be bigger than 7 halves, right? S64 is going to be bigger than 8 halves, right? And you see that it's very, very slow, right? It's very, very slow, right? But every time, if I say 1, 2, 4, 8, 16, 32, 64, right? Every time I take one of those, every time I double, right, then I increase by a half, right? I'm at 1 here, I get half here, I get another 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 half here, another half up here, right? It's very, very slow, but you know, as you go off to infinity, this actually goes to infinity also, right? This also goes to infinity, although very, very slow, right? So what happens is that, right, S of n goes to infinity. Right? S of n goes to infinity, and so in fact, this thing is divergent. Okay. 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 So here are some basic properties of infinite series. Okay. Here's the theorem. If the infinite series A sub k converges to L, and the infinite series B sub k converges to M, and alpha is some real number, then 1, the sum of alpha A sub k turns into A times L. The sum of A sub k plus B sub k turns into L plus M. Okay, so it's just a useful, a useful fact, right? If I were looking at the sum of 5 times 1/3 to the k goes from 0 to infinity, right? Then I don't have to worry about it. I can pull the 5 out, right? I can pull the 5 out, and I get the sum of 1/3 to the k from k equals 1 to infinity. We saw earlier that that was 3 halves, right? And so you get 15 halves. So you can, you don't have to worry. This is a number times the geometric series, so you can pull the number out. Okay, that's what this is saying, right? You can pull, if it converges, you can pull the number out, right? If it converges, you can do these sums separately, right? You can take the sum of the first guy, and you can take the sum of the second guy. Okay. Okay, so here's the last idea in this section. It's something called the nth term test. Nth term test. So, if some of the a sub a converges, then the limit of the a sub k as k goes to infinity must be 0. If your infinite series converges, then the elements have to go to 0. So the way you use it is in reverse. So thus, if the limit as k goes to infinity of a sub k is not 0, we know summation a sub k diverges.